Okay, we have taken another integral. We've got the integral from 0 to 1 of x to the a, x to the b dx. And the reason I was thinking this was interesting is if you just think about when a is 1 and b is 1, this is actually Bernoulli's integral. I did this one before. This is just x to the x. So our methods on this problem today are going to be, it's going to be really similar to this other one, but I just want to get a more general formula for this. In terms of a series, it's hard to get like a nice numeric value or a simple formula for this, but we can put this into a pretty good series form. So for my first step on this, I don't really like having x in the base when we also have x in the exponent. So for x, I can write this as e ln x. And so in our integral with the exponent a x to the b on this, we can write an expression for this. So for a x to the b, using this for x and using exponent properties, I can write this as e a x to the b ln x. And now in order to get this into a series notation, I want to use power series for e to the x. That's going to be our formula for this, is the sum from n equals 0 to infinity of x to the n over n factorial. Now for the convergence on this, it actually converges for all real x, so we don't have to worry about that. Now what we can do for our problem in order to get it into this form, we just have this kind of complicated exponent that we can plug in here. So what we're going to want for this thing, ea x to the b ln x, plugging all this stuff in, we're just going to end up with a x to the b ln x all to the n. But then with exponent properties, let's just distribute the n in and put it on each term individually. And at this point, what I can do is let's just take this whole sum right here. I'm just going to plug it back into the integral and continue from there. And then from here, what I want to do, let's just swap the sum with the series. We can swap this order because we've got our absolute convergence because we started with power series. And now that we're inside the integral here, a few things are constants. So like a to the n and n factorial, those are both constants. So we can bring those outside of the integral. They still have n, so we need them inside the sum. And now what we can do is just focus on this integral here. This one is not too bad. Just using a u substitution. I want to kind of clean up the ln x. That's a little awkward to deal with there. So what I'll do is, we could do u equal to ln x, but what I really want is u minus ln x. A lot of times that works better because when we rearrange it, if I solve for x, x now is going to be e minus u. Then I'll take a derivative for our dx value. It's going to be just minus e minus u du. So I'll go ahead and substitute. First, when you plug 1 in here, natural log 1 is 0. You plug 0 in, natural log 0 is minus infinity, but the minus sign will make it a positive infinity. Another reason to like the minus sign. Now, x to the bn, I can plug in e minus u for that, but then with exponent properties, let me clean this up and I can write it as e bnu. Yeah, it's kind of a lot of variables. So then here, ln x is going to be minus u, so here, I'm actually going to split out minus u and write it as minus 1 times u. This is all to the n, so we're going to have u to the n, and we'll have this minus 1 to the n. And our dx is this minus e minus u du. But then let's use this minus sign right here, and I can use it to flip the bound so we can get it going from 0 to infinity. Now, minus 1 to the n, that's a constant, so I can bring that out front of the integral. And then here we've got the same base. We've got e on both these, so I can kind of multiply them together and add exponents. And then this integral is starting to look pretty good because this is something we could clean up. We could do this with gamma function, or we could do this with a Laplace transform. Either way, we're going to need to either do a substitution or some kind of abbreviation. We just don't like having all this stuff on the exponential. I think what I'll do is another substitution. I'll just try to clean that up. So we'll say, I'll set my t equal to nb plus 1 times u. So then solving for u, it's just going to be t over this nb plus 1. And I'll take a derivative, so the du value is just going to be 1 over nb plus 1. Okay, so one more substitution for the bounds. The bounds are going to stay the same. You plug infinity, it's still going to infinity. Although in order for this to work right, I should have a condition that we want b greater than 0 on it so that we make sure that we're not going to negative infinity here, right? And then you plug a 0 in here, this is still 0. Let me just reverse the order. So for u to the n, I'm just going to plug in all this stuff. So we're going to end up with t to the n over nb plus 1 to the n. All this is going to get cleaned up to the e to the minus t. And then for du, we just need to plug in this dt over nb plus 1. But we have the nb plus 1 in common here. I can multiply these together, and then this becomes an n plus 1 over here. But then for this denominator right here, all this stuff is a constant, so I can just bring this out front of the integral. And then now that we have this all cleaned up, it's set up for the gamma function. In order to use our formula, let me just manipulate it a little bit. For the exponent of n, let's write it as n plus 1 minus 1. And so then our input on the gamma function is just going to be n plus 1. So this whole integral just becomes gamma of n plus 1. But for the gamma function for integer values, and n is going to be an integer, we can put this back as a factorial. So gamma of n plus 1, the formula for this is we just reduce this by 1. Gamma of n plus 1 is the same thing as n factorial. So now in order to finish this off, we'll just throw it all back into the sum. So we've got the sum from 0 to infinity, minus 1 to the n, a to the n, multiply in n factorial over n factorial nb plus 1 to the n plus 1. But then I can cancel out n factorial here and here. And so for my final solution, we just have the sum from 0 to infinity minus 1 to the n, a to the n over nb plus 1 to the n plus 1, and that's it. So as you can see, maybe not the easiest formula to remember. It does get a little simpler for simple cases, like for the Bernoulli integral we talked about at the beginning. That's when a equals 1 and b equals 1. So what's going to happen for that case is you're just going to have the sum. You still have the minus 1 to the n, but then it just becomes n plus 1 to the n plus 1. I think the formula is actually a little bit nicer when we have a equals minus 1. So that would be, the integral would be, so that would be when the integral is 1 over x to the x, or x to the minus x. In this case, you have a minus 1 on the a, so you have minus 1 to the n here. But what happens with this numerator is you get minus 1, put those together, you get 2n. 2n's always even, so this thing's just 1. So then what you're going to have on this is just 1 over n plus 1 to the n plus 1. But now for something like this, I don't really have a nicer way to express it. So pretty much with all the solutions I can think of, we're leaving it in terms of a sum, and then maybe estimating, maybe getting a numerical estimate. But I don't have, it doesn't reduce to like pi squared over 6 or 1 or something. I think the best way is maybe just leave these in the form of a sum and call it good. Okay, so there you go. That's it for today. Thanks everyone for watching. Have a good day.